Example 5. Use the integral test to show that the p-series converges for p is bigger than 1. So this is something that we've already kind of established, is that if p is equal to 1, we have our harmonic series, and it diverges. P is less than 1, we have roots, which means that the denominator is weak, so it diverges. And if p is bigger than 1, that means that it will start to converge. Okay. So we're going to use our integral test for this. So we're going to say that y is equal to 1 over x to the power p. And then we're going to find the area by integrating that function from 1 to, and we need to set up our limit. So the limit as a approaches infinity from 1 to a of 1 over x to the power p dx. So since this is just a power, we're going to apply power rule. So we get limit as a approaches infinity. And we're going to apply the power rule. So this is x to the power negative p. So when we apply the power rule, we get x to the power negative p plus 1. And then we need to divide that by that power. So I'm just going to write it as 1 minus p. And this is going to be done from 1 to a. Okay, so I'm going to input my bounds into this expression. So limit as a approaches infinity. And I'm going to factor out that 1 over 1 minus p. And then I'm going to plug a into this expression. So I end up with a to the power 1 minus p minus, when I plug in the 1 to the power 1 minus p. Okay, so this part just becomes 1. We'll take a look at that. We'll just kind of put that aside for now. We can look at these different parts. So first part we're going to look at is 1 over 1 minus p. Well, what's happening there? Well, if p is equal to 0, p is equal to, not 0, but p is equal to 1. I'm going to put this as an if statement. If p is equal to 1, what ends up happening is we end up with 1 over 0. We divide by 0. That means it's divergent. So when we talk about the harmonic series, that's when p is equal to 1. So when we have the harmonic series, we know that this must be divergent. Okay. So what about this other part here? Okay, so we're going to let we're going to fill this in, and we're going to do the next step. Maybe I'll move this over to the side. And I'm going to plug in my infinity, so I get 1 over 1 minus p, and I get infinity to the 1 minus p minus 1. Okay, so I've kind of dealt with this piece here. So let's see what's happening at this point here. Okay, so this is the second part. Maybe I'll put that up there. So this is, I'm going to label this part 1. So that's the first part that we can look at. There's another part here that we can look at. We're going to call this maybe part 2. So this is the second issue that we can look at. And if p is bigger than 1, so let's say when p is greater than 1, what's going to happen to that expression? Okay, we're going to end up with 1 minus p is going to be greater than 0. Greater than 0 means it's going to be less than 0. If p is greater than 1, 1 minus p is going to be less than 0. This means it's a negative exponent. It's a negative exponent, means that we're going to end up dividing by infinity. So that means it is finite and convergent. This is what we've known from that p-series test, is that if it's bigger than bigger than 1, the the p-series converges. Sorry, not the power series, the p-series converges. Okay, so then we have this other situation, so that we'll call that A, and B is when P is less than 1. When that happens, P minus 1 minus P must be bigger than 0. It's a positive exponent. If it's a positive exponent, then that means that expression ends up with infinity to some power. We'll call that, infinity to the power n. Okay, that means then it must be divergent because it's infinite sum. Or in this case, it's an infinite area, which we can translate into an infinite sum. We can summarize this then by categorizing these as our divergent types. When P is less than 1, it's divergent. And if P is equal to 1, it's divergent. And if P is greater than 1, this is where we have our convergent series.